Okay, just a quick video. A few people have been asking about the next assignment for Unit 35. So I just thought I'd go through, I produced a practice one and I thought I'd just go through it quickly for you. So the first question is, we've got to draw, you're going to get 3 logic gates that you've got to draw the symbols for, you've got to produce the truth tables for them, the Boolean expression, and explain the operation of them. Okay, so let's just kick straight off there with that. So so our NAND gate then, our NAND gate looks like this. I'm just going to give it some identifying legs. Therefore, then I can do the truth table for it like so. Okay, 0, 0, 1, 0, 1, 0, 1, 1. And because it's a NAND gate, then we're going to get an output like that. I'll leave you to it. Obviously, if you didn't recognize that as a NAND gate truth table, you need to obviously go back and look at that. The Boolean expression for it is Q is A and B, because it's and then it's the whole thing is knotted. And then finally, how does it work? Explain the operation. Well, so I can see it quite simply say any input is low, the output is high. And that's the first NAND gate done. Okay. Okay, I've just done exactly the same for a NOR gate. So that, oh, I haven't actually. I need to put a circle on there. There's my NOR gate. Truth table for it. So opposite flipped inverted one for an OR. And then we need to put our line above our A or B or knotted. And then finally, you can see from the truth table, if any input is high, then the output is low. And finally, I'll finish off with a NOT gate. And there we have it for a NOT gate as well. Marvelous. Let's move on to the next question. Okay, next task then. We need to produce a truth table for this circuit. We need to derive the Boolean expressions for this part of the circuit, build the circuit on Circuit Wizard, or the online package. I'm not going to do that bit, and then you need to confirm the operation against the truth table. Okay, I'll talk about that once we've built the truth table. Swings around about whether you do item 1 and 2, which one you do first. Derive the Boolean expressions for each part of the circuit or do the truth table. As it's there in front of me, I'm going to derive the Boolean expressions. Okay, so we've got K going into this. This is a NOT gate, so the output M there then is going to be NOT K. That K then feeds into this OR gate here. So the output N from the OR gate then is going to be NOT K or J. We've got an AND gate here that's got NOT K going into it. So NOT K and L. And then finally we're putting it all together for T. So NOT K or J. Okay. Or NOT K and L, all knotted. There we have it. Okay, so let's do draw the truth table for this circuit. Give me a second just to draw this out. Okay, so I've drawn the truth table here. I had put it sort of on the next page, but then I'd end up flicking backwards and forwards. So I've got my inputs J, K, and L. Okay, and then I've got M, N, X, and T. So all I'm going to do is go through each line by line, popping it in. So M then is the inverse of K. So whatever K is, so therefore I can pop that in. So it's going to be 1, 1, 0, 0. Okay, and there we have M finished. Okay, so it's just the inverse of whatever K is. Now N has got, and this is where we move away from what we've got on here and we just look at the different inputs. So N is an OR of J and M. So I just need to look at these two columns, J and M, and then OR what we've got. Okay, so there I've just gone around it. So we've got so J and M. So whenever we've got a 1 there, a 1 there, so we can put a 1 and a 1 there. Zeros, we've got 1 there, so put a 1 there. A 1, a 1, so there's 1 there. 0, so 0 there, and then we've got a 1 here, so we've got a 1 there. Right, X. What is X made up of? X is an AND of M and L. M and L. So I'm looking at the M and the L column only. Okay, so that was easier than I thought. So the first 4 lines, because we're looking at the L input at 0, 0, 0, so we're always going to get a 0 out for those 4. Okay, then, and then M is high there, so we're on 1s, then it's low, and it's low, so we've got 2 lows there finally. And then T. T is a NOR of N and X. Now remember, for a NOR gate, we're looking for, to get an output high, both of these need to be low. Both of these need to be low. Okay, so there's our completed truth table for it. We've already derived each part of the expression for the circuit. So we're then going to build this circuit on the simulation software. So you can use Circuit Wizard or you can use the Academia stuff. And then what you're going to do then is you're going to confirm against the truth table. How are we going to confirm against the truth table? So if you have this input, you should get a 1 out. If you have this input, you should have a 1 out. So all other inputs then should be 0. So you just need a couple of photos there to show that it is doing as you've said it's doing. Okay, so the next task here, we've got to modify 2 of the logic gates only so that we match what we've got here. I suggest that actually you don't actually even need the circuit. You can just look at what you've got. So what we've got here, so it's still going to be exactly the same layout. So M is still going to be is dependent on K. So you can see there it's 0, 1, 1, 0. So so the output M, that is still going to be our NOT gate. N is dependent on J and M. So I'm just going to write that in there, J and M. So it's dependent on those 2 inputs. N is dependent on J and M. Okay, so if I look at J and M, so I get a 1 out when I've got a 1, 1. And that's the only time that I get an output as a 1, 1. So there's a couple of logic gates it could be, but if I look at then at a 0, 0 condition, I still get, on that one I get a 0 out, so it can't be exclusive NOR, so therefore it must be an AND gate, and before it was an OR gate, so it's been changed to an AND gate, right? So X is dependent on M and L. X is dependent on M and L. Can you see that? So X here is dependent on M input and L input. So when we look at the M and the L input, so if we look at the M and the L input, we've got L all zeros there, and we've got zeros out, and then if we're looking at the M input, zeros getting 1 out, but then when we got M and L both high, we get 0 out. So it looks like whenever you've got a 0 on M and L, and you're going to get a high out. So that makes that a NAND gate. Okay, and then T, just double checking. So T is dependent on N and X. So N and X. Now it said only 2 gates have changed, so it should still be a NOR. Let's just double check that we've got. So in the NOR gate, both inputs are 0. We get a 1 out. Okay, so that's it. Both inputs. So that's still a NOR gate. A NOR gate. So that's fine. And then we do exactly the same idea. You build this on Circuit Wizard or Academia, and then you can then swap those 2 logic gates out and confirm with some photographs that when you have 0, 0, 1 on your inputs, you're going to get a 1 out. Okay, and again it says minimum of 3 shots. So you need at least that one and then a couple of the others. And that was that question. Nice and simple. Right, okay. Okay, task 4. So draw the logic diagram in full on Circuit or Academio for the Boolean expression. So we're drawing it out in full. So let's draw it out in full. So the first of all, I've got A and B inputs, and they then go into a NOR gate. So I'm going to just draw it out. You'll obviously draw it out on things. So I've got A and B going into a NOR gate. So there's my NOR gate, like so. And therefore then I've got my A and B. So that's A or B all knotted like so. Okay, what does that feed into? Well, I then have a connection that goes to another logic gate, which looks like it's an AND gate. Okay, and into the AND gate I'm going to have a C input, and then I'm going to have a NOT A. So a NOT gate there like so, and then that connects there like so. That was a bit rubbish connection, but so I've got NOT A, so that's my NOT A, ANDed with C. And what does that all connect into? It looks like it connects into another, connects into a NAND gate because it's ANDed there and it's all knotted. So therefore I can draw my NAND gate and all knotted, and then just to double confirm that what I've got matches. So that's ANDed with NOT A, C, and then it's all inverted. So by building it up step by step, you can confirm what you've got. So just draw what you see. So draw that little bit, and then draw that little bit, and then how do they interconnect? Okay. So we've labelled each part of the diagram. Okie dokie. So what I've done, I've just drawn out a quick truth table here. I've labelled various points, so it makes it easier for mapping it across. So therefore, we're going to do exactly the same exercise as we've done before. So let me quickly just do that. So there's the R input, which is a NOT of the A, and there's the S input, so the S output, which is an AND of whatever of R and C. So zeros, zeros. So when R and C are both got to be high to get a 1 out. And then T is a NOR of A and B, so both A and B have got to be low to get a high out. So let's just do that. So there's my T, and then Q. Q is from a NAND gate, so we're looking at T and S. So if T and S, any of them are low, then we're going to get a high out. Okay, so there we have our final truth table outputs. Marvelous. What else are we going to do? So it says we've got to check it against the circuit. Okay, so we need to just confirm that that's what we got. So from our built circuit, do we get a low output when we have that condition and the rest of it? And then we've got to then produce a Carnot map to produce the minimized expression. So there's my framework for my Carnot map. Okay, and the easiest thing for me to do is to plot this 0. So I'm looking for when A and B are 0 but C is high. C is high and A and B are right. So we've got a 0 there, and then everything else is high like so. Marvelous. Now we need to then do our circle, so we're looking to circle it in the largest groups possible. Okay, so I've just drawn two circles there, so circling there like so. So a group of 4 there, a group of 4 like that. Okay, notice I haven't captured that one. Okay, so that you might be there tempted to just do it as a circle on its own, or a circle as 2, but actually no, we can circle that as a 4 again. Okay, so let's see what we've got. So Q is equal to, if we just do this top circle here is not C. If we do this circle here, then what stays the same? Then it's going to be A, and then in this last circle, then it's B. Let's just look at on our truth table here. So we've got zeros, we've got ones out. Whenever A is high, we get a 1 out. Okay, so A is high, we get a 1 out, which then covers off these two. And then finally, when B is high, which covers this one out. So you notice that that one still is correct. Fabulous, fabulous. What else we're going to do? So then we've got to build the simplified diagram, circuit diagram, and check against the truth table in question 2. So the truth table that we produced here, is it correct? I've just proved it there, but in my head, but effectively, we're just going to have, and you can do it. It's up to you how you want to do it. I could just have a massive OR gate, or I could have A going into an OR gate with B, and then I've got a NOT gate there with C, and that's how I would have drawn it on a circuit like so, and I can confirm that what I've got. Okay, more photos and stuff. Right, there is one more task to do after this, which is a research task. I'm not going to go through that in the video. It's a research task. Okay, have fun. Bye.